Today we'll talk about elasto plastic bending. And for that, we consider a material which is elastic perfectly plastic, which basically means it has some slope in the elastic part, and in the plastic part, it is completely flat once it reaches the yield stress. So, for the sake of simplicity, consider a rectangular cross section for the beam, which is let's say B times H, and also consider, now this can be based on the problem that you solve. Okay, it's not working. Okay, so imagine it is simply supported and you are applying a force exactly in the middle. Okay, so so can you draw the shear force and the bending moment diagram for this one?
Yes, sir.
Okay, so go ahead and draw the shear force and the bending moment diagram. Okay, so for that we need, first of all, there would be two reaction forces, R1 and R2, and if X exactly in the middle, there is no way these two reaction forces are different. Now shear force diagram would depend on from which side are you drawing it. So it's going to be, let's say if I draw it from left to right, it is going to be this. Or if I choose it to do from right to left, it is going to be different. But when it comes to the bending moment, it's going to be same from each side. I mean, from both the sides. Whether you draw it from left to right or right to left, it is going to be the same. Okay, so we realize that the maximum bending moment occurs uh, at x equals L by 2, that is in the middle of the beam. Okay, and how much is that bending moment?
FL by 4.
It is F by 2 times L by 2, right? So FL by 4, as you said. Okay, and see this part of the analysis. Okay, this is only based on the equilibrium equations. We are not talking about any form of deformation of the beam. And if you recall your study of beam, okay, this relations would be same even if the material were rigid. If the beam were to be made of a rigid material, then also you are supposed to get this sort of answer. Because we have so far not talked about stresses and strains, but now we would. Okay. So the idea is, if I cut it anywhere, okay, if I cut it anywhere, I'm going to get yeah, I should be drawing a larger diagram. So if I cut it anywhere, so I'm going to get some stresses, right? And let's say with the example of a rectangular beam, we know some stress distribution that we are going to get. Okay. Now this is typical of the within the elastic limit. Okay. So this is how the stress distribution would behave within the elastic limit. Okay. And actually, to be precise, this distribution holds true for strain, whether or not you are within the elastic limit. So this is how the strain changes. Okay. And this, by the way, the point where it intersects with the y-axis, or where the value is 0, is called a neutral axis. I mean, if I take the locus of those points across the different cross sections, okay, so that axis would be called neutral axis. In a way, there is a neutral plane if I draw it in 3D. So if I were to draw it in 3D, I would get a neutral plane on which so on this one, the strain and stress is supposed to be 0. Okay. Now, when it comes to rectangular geometry, that region should be the center. Okay, I mean, this portion is h by 2 and this portion is h by 2. Now, why is strain supposed to behave like this? It's because, you see, if you consider the geometry to be made of layers of materials, okay, so, and they are connected with one another, okay, then they are supposed to I mean, they are bound to, deform like this. Okay, so at the neutral axis, let's say the radius of the neutral axis is rho. So at the neutral axis, uh, the deformation is 0. Okay, but if you go below neutral axis, let's say by a distance of y, Okay, so you develop some strain, and that strain is simply proportional to y, and because of that the strain would be changing linearly across the cross section. It's just that the position of the neutral axis would depend on what sort of cross section do you take. Is it a rectangular cross section? Is it an I section? Okay, so on all of that would depend where is the position of a neutral axis, but more or less the um, for a prismatic section, that's the kind of relation that you can expect for the strain to vary linearly across the section. Okay, now this also means that within the elastic limit, this is how the stress changes. Okay, so this is how the stress changes. Let's call it sigma star. Now if the bending moment of a given cross section is x, can you tell me what is the relation with the stress sigma star? So the stress at a given x, that means at a given cross section, the stress is
Given
simply
by I is
sigma
y.
star times y by h by 2. Yes, you're saying something.
We will not use that equation, bending moment equation, that sigma by y is equal to m by I.
Yes, I know you know the formula. Sigma equals my by I. Okay, but can you tell me, is it which stress this one is? Is it the stress, you know, the maximum stress in the cross section, or is it the maximum stress anywhere on the beam? Which stress this one is?
Depending on the m, that is in anywhere on the beam.
No, I didn't get
On the
your answer.
moment.
I, ho-
Actually, depending on the
I don't think you also got my question. My question is, this sigma over here, which stress is it? Is it anywhere on the beam? Is it the maximum stress in the cross section, or is it the maximum stress anywhere on the beam?
So when y is equal to b by 2, then it's maximum stress on the cross section of the beam.
Okay, which means this answer is what? This is a stress where?
Anywhere in the cross section of the beam.
Anywhere in the cross section of the beam. Okay, uh, and and I know you know this answer. Okay, but I just need you to be able to derive this, because you see, this relation holds in, as I said, within elastic limit. So the point is that unless you know how to arrive at this equation, okay, you would not be able to get the expression with plasticity. Does that make sense? I mean, how do you get the expression with plasticity? What happens? Can you tell me what happens with the plasticity in the expression for the stress? You simply
yielding
don't.
will take place.
Yes, of course the yielding will take place. But my question is, do you know the expression for the stress? In plasticity, of course, the plasticity happens after there is yielding. I mean, you are supposed to solve problems, right? You are supposed to do math. And unless you know the expression, you cannot do that. Simply saying vague answers like there would be yielding or there would be plastic deformation is not going to serve anyone. It's not a viva. So we know that the stress in elasticity would be your proportional uh, to to your distance from the neutral axis, and if at the two ends the maximum stress is sigma star, so we have this expression. So as we integrate this quantity, you need to think in this way. Let's say this is the cross section, and ideally I should be drawing the rectangular cross section because all of this derivation is for the rectangular cross section. But you see that the relation that I'm about to get is general, and I can do that for general cross section. So go anywhere on the cross section, you will have the differential area. And in that differential area, let's say this is how the beam extends. This is the beam. Okay. And yeah, this is not how I should be drawing the neutral plane. Okay, so this is a neutral plane. And let's say this is your distance from the neutral plane, y. Okay. And in this case, let's say this is the stress sigma on it. Okay. Acha, one more thing before going into further detail. Can you tell me whether so this type of configuration of the beam is called 3-point bending. Now in 3-point bending, are we supposed to experience pure bending? Is it pure bending? Do you understand what is pure bending?
Sir, aim constant सर्व शब्द.
Okay, but is aim constant?
No, sir.
No, right? The actual answer is in order to have pure bending, I mean, the pure bending need not happen across the entire beam. Okay, it can also happen at a very small region. But whatever that region may be, there the shear force should be 0. Okay, and if you really think about it, if you really think that this force F over here happens across a finite area, that means the shear force would be changing linearly in this region. Okay, and I mean, it's not, a step, it's a gradual change, and somewhere it would intersect, basically in the middle it would intersect with the x-axis, or basically the shear force would be 0. So basically the very tip that you're looking at, okay, that's where pure bending is happening. So it may not be happening anywhere else on the beam on 3-point bending, but where the maximum bending moment is, there it's maximum because it's maximum as in the bending moment is stationary at that location. It is maximum because shear force is 0. As you might recall, dm dx is v. Okay, so it is maximum, bending moment is maximum because the shear force is 0. So it indeed there is pure bending in the 3-point bending situation as well, but that's just to a single point, not anywhere else. Acha. But then there would be, but for everywhere else, okay, you can think of there is shear stress due to bending. And can you tell me what is the expression for the shear stress? What is the expression? V times shear force times?
Sir, A into Y by IB. V into A into Y by IB.
Not A into Y. There was something called Q and then IB, right? So Q is, let's say you are, Q is the first moment. What is Q? Let's say you have a cross section. Okay, so, and let's say this is your neutral axis. So what do you do? Let's say you are trying to get this Q as a function of Y. So this shear stress is a function of Y. So at Y, what you do is you calculate the first moment for the area. Okay, which area? From the top to this height of Y. Okay, so for this shaded area, you calculate the first moment. What is first moment? First moment is integration Y dA. Unlike I, which I believe is integration y squared dA. But that would be happening over this region, this area called A prime. Okay, this shaded area. And as it turns out that if you do it at the very top, there you don't have any area, right? Because if you take Y to this height, there is no A prime area. So QH by 2 is 0. But then if you reach the negative one, okay, so that also becomes 0, because you see you are integrating y dA, okay, and the y is considered from the neutral axis, and the neutral axis is supposed to pass through the centroid, which is y bar x bar, or sorry x bar y bar. Okay, but according to the coordinate system taken from the neutral axis, x bar would be 0 and y bar would be 0, because the neutral axis is supposed to pass through the centroid. Okay, and basically integration y dA across the entire area, if A prime is A, that means you are calculating this quantity Q at the very bottom. Okay, that means you are covering the entire area. So if you do this integration y dA over A, that basically is A times y bar. But please understand, this y is being considered with respect to the neutral axis. So this y bar is also with respect to the neutral axis. So this is the coordinate of the neutral axis as measured from the neutral axis, which basically means this quantity is 0. So this quantity again becomes 0 at the very bottom. It is maximum at the neutral axis. Okay, so so can you tell me, you understand that V is either f by 2 or minus f by 2 maximum. Sorry, V is this much. Okay, so V is plus or minus F by 2. Okay, and Q max is this quantity integration y dA. Okay, let's say for this rectangular cross section. Okay, so can you tell me what is the maximum value of tau y, shear stress due to bending? Can you calculate this? So just calculate Q at 0. So Q at 0 basically means integration 0 to h by 2. Your dA is this portion, b times dy times y. Okay, and that multiplying v, but then you are dividing with I times q, sorry, I times b. So the two b's cancel out. Okay, so you only need to do integration y dy dividing with I. I, by the way, is the second moment, and I believe this is the expression. Okay, so it is not the expression for Q. It is the expression for the shear stress maximum. So maximum shear stress due to bending. Now please understand that the shear force is kind of constant. Whether you look in the left or in the right, shear force is a constant, and because of that, tau max only needs to be calculated across a section. Okay, and tau max for this section is also the tau max for this section, because it is not changing with x. Tau max would not be changing with x. It would only be the maximum stress in a given section. So can you evaluate tau max?
V O square by 8I.
So tau max, you are saying v y squared. No, you would not get an expression of y squared.
3 by 4 F by BH.
3 by 2 V by BH.
Okay. So you can also write down the expression for v, right? So is it this?
Yes, sir.
Yes, sir.
Okay. So that q you evaluated by integrating from 0 to h by 2, right?
Yes, sir.
Q by b. So it is actually tau is v by I, q by b. So v by I you can understand. So q by b would be this expression, right? So I'm just taking this for a representative value. Okay, so it need not be exactly accurate, but more or less the dimension looks correct to me. So this is force, and you have twice the dimension of length, so kind of matches with the dimension of the stress, which is fine by me. Now look at your very familiar expression, okay, of the bending moment, which would be, sorry, not bending moment, the normal stress due to bending. So for that, let us take the maximum bending moment, and we just established that was F by 2 L by 2, and then H by 2 for the maximum Y, and then 1 by 12 B H cube. Now can you tell me what expression do you get? So F by 2 times L by 2 gives you the maximum bending moment. Then this is maximum Y.
So 3 by 2 into FL by BH square.
There is a reason I'm writing it like this. Okay, so this is the maximum shear stress across the beam. This is the maximum normal stress across the beam. Okay, just consider the two values. This is kind of twice of this quantity, right? 3 by 4 BH. But what about the next term? If the beam is really slender,
তো বি এইচ স্কোয়ার হবে না?
sorry, so if it is BH squared, so yeah, this, right? F by BH, L by H. FL by BH squared, right?
হ্যাঁ স্যার।
Yes.
So my point is compare this with this, but take this one out. Okay. So this is an additional multiplication. So basically, my point is for a slender beam, which is that is a very thin beam, okay, has a thin cross section, much thinner than its length, then I mean, for a condition where it can be really called a beam, so H by L, okay, is much smaller than 1, or H is much smaller than L, okay, which is H by L is much greater than 1, okay. And let's say if I take H by L actually 0.1, then tau max is only 1 in 20 of sigma max. Now, why am I doing all these calculations? You see, in plasticity, so we learned about yield surfaces. And yield conditions. For example, if we are to use Tresca criteria, we need to get the principal stresses. Okay. So if we have certain sigma x and sigma y of course is 0, then certain tau xy, this time I'm drawing the Mohr circle, you know what to do, right? join these two and draw a circle. Rather, draw the more circle. And that is supposed to give you sigma 1 and sigma 2. Okay. Or the maximum shear stress or sigma 1 minus sigma 2 by 2 is your square root of sigma x by 2 whole squared plus tau xy whole squared. Okay. And if you are dealing with von Mises criteria, this is how you get the equivalent normal stress. So you need to compare this tau max with tau y in plasticity. So over here it is simply one by 2 so sigma x is non-zero, sigma y is 0, and sigma z is 0. Plus three times we'll have to also consider tau xy squared. Of course, tau yz and tau zx are 0. Okay, so the point is this should be less than equal sigma y. So the point is that tau xy also comes into the calculation of the equivalent stresses. Okay. Now, if h by L is around this much, okay, in order for the beam to consider to be slender, then tau max is this much, right? And in a situation like that, you can imagine how much is 1 by 20 squared, right? If this one is 1 in 400, okay. And then you can practically neglect tau xy in our calculation. Not just at the maximum bending moment, anywhere in our calculation. So we are simply using the pure bending assumption. Okay, because tau xy or even the maximum shear stress, okay, you do realize this is not everywhere. Okay, so only in the neutral axis is this maximum. Everywhere you have this situation where you can simply neglect the shear stress due to bending. Okay. Does this make sense? I mean, this will simply help us in doing the mathematical part, okay, because it makes our calculations a lot simpler. But the idea is we need to get rid of tau max from our equations. And if we do get rid tau max out of our equations, so the sigma equivalent is effectively sigma x. And that's what needs to be compared with sigma y. You understand, if this tau xy is much smaller compared to sigma x, I can simply ignore this. Okay. So if h by L is, let's say 1 in 20, okay, or so then this relation should be around 1 in 1600. Okay, because then this should be 1 by 40. Okay, so you can totally neglect, for all engineering purposes, you can completely neglect this portion of it. Okay, so of course the sigma max and tau max do not happen at the same location. Okay, so the comparison can be with respect to sigma x with sigma y. Now this sigma x is the the normal stress in x direction, and this sigma y is the yield stress. Okay, and if it does confuse you, let's call it um, sigma yp.
মানে স্লেন্ডারনেস রেশিওটা চেঞ্জ করলে কোনো
না না
এতে
না,
এফেক্ট
এখানে
করবে
কোনো
না?
স্লেন্ডারনেস রেশিওর কথা বলাই হচ্ছে না। স্লেন্ডারনেস রেশিও, we talk about slenderness ratio in relation to buckling of column. Okay, and that would have the characteristic radius. Okay, I mean, sorry, you get the radius of gyration of the cross section, which is the characteristic radius of the cross section divided by 2. Okay, and that and you divide the length of the column with that radius of gyration, and then you compare. Okay, I'm not going into that slenderness ratio, I'm just going to the comparison that for a slender beam, okay, where the height and the width of the beam are much smaller compared to the length, do you agree that for all intents and purposes I can neglect the shear stress due to bending from my calculations?
Yes, sir.
Okay, also you need to note one more thing, that the maximum bending moment happens at the cross section where the shear stress is supposed to be 0, because the shear force is 0. And why is the shear force 0? Because the bending moment is maximum. Okay, the derivative has to be 0. So it is already pure bending. But if I go for the rest of the cross section also, there I can neglect the shear stress due to bending as compared to your normal stress. Okay, so with that we'll begin our calculation. Now let's see how do we get that bending stress expression, which is my by I. Okay, you see sigma is sigma star, or the maximum stress in the cross section, times y divided by h by 2. Okay, and as well, I was saying that you have the cross section. Okay, and let's say this is a neutral axis from which I'm measuring the distance of this differential area. Let's call this area as dA, and let's say the stress on that differential area be sigma. Okay, so sigma is anywhere on the cross section. So the differential force due to differential area is sigma times dA. And how much moment does it produce about the neutral axis? Differential moment is y sigma dA. Okay, now if I write the expression for sigma, that would be sigma star times y square by h by 2 times dA. Now if I integrate this dm, okay, as you know, the stress is the response of the material, or stress is the way the material is trying to support that moment, bending moment. Okay, so that must equal to the bending moment of the cross section, this one right here. So if I now do the integration across the area, sigma star and h by 2 comes out of the integration because they are constants, and then I am left with I, integration y squared dA. Okay. So that is the expression for sigma star. Substitute that over here, and you have my by I for any arbitrary prismatic cross section. Okay. So just keep this in mind. All we have to do is balance the moment in the cross section. Okay. Now imagine as I increase, if sigma increases, okay, and after a certain point it would reach the sigma y value or sigma yp value, the yield point value. Now what happens after that? The stress cannot increase further. Okay. So what happens in the cross section is that you see the strain, because the deformation is such that the strain must increase like this: epsilon max, epsilon mean, which is minus of epsilon max. Okay. And this is the y coordinate measured from the neutral axis. The stress, on the other hand, does this. How does stress change with strain? It is elastic, perfectly plastic, right? So it becomes flat beyond yield stress. So where on the cross section, where on the beam you reach yielding first? So if you have the entire beam, in that entire beam, at which point do you have the first yielding? The answer is simple: wherever the stress is highest in the elastic, within the elastic limit. And that is for a 3-point bending situation, that is in the middle and at the maximum heights. There, right there, is where you reach the yielding first. Okay. But then what should be the value of F? F at first yielding. So in the entire beam, when the first time yielding happens, so for that you need to have the sigma max. What I mean by that is, you go to the cross section where you have the maximum bending moment and go for the maximum height and divide with the I. I, of course, as we discussed, 1 by 12 bh cube. Okay. And bending moment, maximum bending moment, as we discussed, was this quantity, right? Okay. Now, when first time yielding happens within the entire beam, the meaning of that is, that's when this equals sigma y. The maximum bending moment, bending stress anywhere on the beam, okay, which is in the middle and at the top within the elastic limit, that just turns out to be sigma y. Okay. So can you calculate the expression for F? What would be the expression for F? I mean, substitute the expression for I as well.
Three by two BH square by L sigma y.
3 by 2. Then,
Yes, sir.
then
BH square BH square by
x
L
b
BH
squared.
square by L
Acha, bh squared
BH square
by
by
L.
L
Then
sigma y.
sigma y.
Sigma y.
Okay. Okay. So, so make a note of this expression. Okay. So that is the f value at which first time that is at this force value, plastic deformation starts within the beam. Okay. Acha. Or the first time the yielding happens.
স্যার এটা 2-3 হবে মনে হচ্ছে।
Is it 2 by 3?
Yes, sir.
Okay.
Yes, sir. 2
Okay.
by 3.
Okay. Maybe. Okay. So 2 by 3 BH squared by L times sigma y, right? Okay. So next thing is, I'll erase everything from here. Next thing is, so imagine that cross section where you have the maximum bending moment. What happens to it now? The strain is still going from minus epsilon max to plus epsilon max. Now, stress changes with strain in this pattern up to yield point, proportional, and then beyond that it becomes flat. Okay, so never in this exercise would we ever calculate the strain, but we need the representation for I mean, to find the distribution of stress, we need to have this. Now let's say if has gone beyond that that earlier f prime, which is your 2 by 3 bh squared by L sigma y, which marks the initiation of plastic deformation in the beam. Okay, now imagine f has gone beyond that. Okay, so can I expect a stress distribution? You see, the strain is proportional to y. Okay, so stress changes with y the same way it changes with strain. Strain is proportional to y. Strain changes proportional to y. So stress changes with y just the same way the stress changes with strain. Now, does this statement make sense to you?
স্যার একবার বললে ভালো হবে।
You see, strain, whether elastic or plastic, okay, strain changes with y proportionally. Okay, I mean the total strain, whether in elastic deformation or plastic deformation, it has to change proportional to y. Okay. Now, what about stress? Then stress would change with y exactly the same way it changes with strain. Because you see, strain is proportional to y. Does that make sense?
Yes, sir.
Which is to say that the stress distribution would look like this. What do I mean by this? The two extreme values are plus and minus sigma y. Again, there is an assumption that the yield stress in compression is same as yield stress in tension. So this is what now the stress distribution should be. So there would be an inner core, okay, which would have elastic deformations going on. And then there is this outer shell, there is this inner core, which is elastic, an outer shell, which is plastic. Right? So now, how do you get the stress distribution as a function of y? Given that, I mean, how does that relate to bending moment? Bending moment, of course, relates to, bending moment, of course, relates to F through this relation. Okay. Now, F has gone beyond that critical value at which the yielding starts. So F has gone beyond F prime. Okay. Now, how do you relate between these two quantities, this F right here and this C right here? That means the size of the inner core, okay, and the applied force. For that, you should be in a position to relate between the maximum bending moment. Okay, I'm still considering that central cross section, the middle cross section. Okay, I'm still considering that middle cross section. Okay, so now how do you relate between? I mean, actually, you can do this exercise for any cross section. Let's say you can do that calculation at x equals 0.4 L instead of 0.5 L. But I'm still doing that at 0.5 L. Okay. I mean, if it is 0.4 L, if you simply write it to be 0.4 L right here. If it is not, if it would not be F by 2, L by 2, it would be F by 2 times 0.4 L. Okay. But then you'll have to also, identify the force value at which the yielding starts at 0.4 L. Okay. So, but right now I'm just doing it in the middle. Okay. So the next thing is, I should be in a position to relate between the maximum bending moment. আচ্ছা এই পার্টটা কি বললাম বুঝতে পারলে যে you see the plastic deformation just not only happens at the middle cross section. Let's say this is the middle cross section. It can happen over a range of cross sections. Okay. And you can actually identify the stress distribution for a given F value, okay, at any cross section. But for that, you need to identify what would be the force value, okay, for yielding to start in a given cross section. Let's say this is 0.4 L. Okay, so over this cross section, okay, you can do the math for how much force value do you need to have yielding started. The answer is very simple. That is going to be, let's call it F double prime. That would be 1.25 times F prime, simply because the bending moment is proportional. Okay. Now, now I'm not doing all of that. I'm simply, considering the middle cross section. Now, in the middle cross section, the bending moment expression is this, and that must equate to integration sigma y dA over the area. Okay. Now this actually is twice, you see, it would be twice sigma y times y b dy. So b dy is actually your differential area, and the range actually is from c to h by 2. You see, it happens on both these sides. That's why I'm just multiplying with 2. Okay. So bending moment, you can imagine what happens to the other side. Okay. The stress is negative. Also, the y coordinate is negative. Together, they will be making positive quantity. Okay. So this integration just happens twice. And then the other term, where I need to put 2 once again, because the integration is from minus c to c. So twice 0 to c, but this time the stress is sigma y times y by c. You see the stress is changing proportional to y. Okay. So in this region, the stress is sigma y times y by c, then y, b, and dy. Okay. YB dy is coming from here. But the expression for the stress is different in two regions. For the shell, for the hollow shell, this is simply sigma y everywhere. For the inner elastic core, it is going to be proportional to y coordinate. Okay. Now, can you integrate these two quantities and have the expression for, let's say, let's call this, have the expression for f. The value of f, required to produce an elastic core of size twice c. Can you get the expression for f? Did you understand the question?
Yes,
Yes,
sir.
sir, good. See.
Okay.
F is equal to 8 sigma I B divided by L or bracket h square by 4 minus c square by 2 plus c cube by 3.
F equals, so sigma y times b times c squared, okay, that would have a coefficient of 5 by 3, right? No, not 5 by 3. One by 3. Then sigma y b, sigma y b times h squared by 4. Is it the expression?
Yes, sir. At 4 by L multiplied হবে
4 by L multiplier.
Okay, okay. This whole thing gets multiplied with 4 by L. Okay. So 4, actually, this whole thing multiplies to 4 by L. So, yeah. So it is 1 by L sigma y b. Okay. Okay. So we can get the expression right. So it is sigma y b by L, then h squared minus 4 by 3, 4 by 3 c squared, right?
Yes, sir.
Okay. So in this expression, substitute c equal h by 2. In this expression, substitute c equals h by 2. What do you get? So if the size of the elastic core, okay, extends to h by 2, and plastic deformation has just begun at the outer fiber, so f of c equals h by 2 should be f prime, right? Is that what you were getting?
Yes, sir.
Okay.
Yes, sir.
So that only tells you that your expression is correct. I mean, consistent formulation. Okay. Acha. Now, can you tell me, can you answer this question? What is the maximum load bearing capacity of the beam? Can you answer to this question? And that would also answer why we are only, focusing our understanding on the middle cross section. Now, how much maximum load can you put to the beam? You see, You see, when the stress distribution is like this, you cannot go beyond this situation. That means our source of stiffness, what is stiffness? Stiffness is not defined by the maximum load. Stiffness is defined by the fact that if I produce more deflection, does it produce more resistance? Now, the beam's ability to produce more resistance ends when the entire cross section has become plastic, or when C has become zero. And that actually we would call as, let's say, F star, the maximum load bearing capacity of the beam. You cannot produce any further F because there is nowhere to accommodate more stress. Everywhere in the section, there is the maximum stress, either plus or minus. So the stiffness of the beam has just become zero. If you produce more bending, it cannot produce more resistance. Or in other words, it doesn't need any further increase in force to have any arbitrary amount of deflection. The stiffness has just become zero because it has reached its maximum load bearing capacity. Okay, so I'm going to give you an assignment. The assignment is B equals 50 mm, H equals 5 mm, L equals 1 meter, and sigma y equals 200 MPa. Okay. So I need you to be able to plot C versus F in an Excel sheet. Of course, the functional representation is F with respect to C, but once you take a bunch of C's, okay, so C goes from H by 2 to 0. Okay, so this is going to be kind of a relation like this, or maybe like this. Okay. So value of C kind of represents your load bearing capacity. Okay, and once you are closing up on the core, this just happens faster and faster, and you reach the F star value. Okay, so I need you to plot this in Excel. Okay, and once you do, okay, take a snapshot of that and post it in the classroom. Okay, so do this assignment, get the solution, and post it in the classroom. C versus F plot.
Okay, sir.
Okay, acha. Now, in the semester, you might get a question that find out the F value at which you are getting C equals H by 4. Okay. So can you tell me what is the F value for that?
Sir, 11 by 12 sigma y b h square by L.
Okay. So it is easy to calculate, right? You just simply substitute the expression for expression for C, right? Now the question is, now the question is, what are the residual stresses? So the thing is, let's say with yielding you have reached somewhere over here. Okay. And now you start unloading. And as you might recall, the unloading window is the elastic window of unloading happens elastically, and that window extends to twice sigma y, which basically means, what is the F value that you mentioned? F equals sigma y b by L times h squared. What is the coefficient?
11 by 12.
11 by 12. So let's say this is the F value, okay, from which you are unloading. So your F unloading would be, so you are unloading this much F. Okay. Now the reduction in the stress is going to be elastic, and delta sigma, the reduction, is going to be the stress anywhere on the cross section corresponding to F unloading. You see, right now, without unloading, this is the expression for stress you have. Okay. I mean, it should be, okay. So once you go beyond this value, h by 4, it is simply sigma y. Okay. The more generalized expression should be sigma y times y by c, and sigma y for this less than c and this greater than equals c. Okay. Now arbitrary core dimension. Okay. Here I have just chosen that this c becomes h by 4. Okay. That has been chosen. But for an arbitrary value of c, okay, this is the expression. Okay, don't just make this as the generalized expression. This is the generalized expression. Now, if this much is your unloading force, what is the unloading moment? That would simply be and the stress, you might recall, okay, was m times y by I. Okay. So substitute for all of this expression and get the expression for delta sigma. So when you are, you understand, right? When I'm doing an uniaxial tension, everywhere on the cross section, it's the same stress. And then when I remove the force, okay, everywhere in the cross section, you end up having the same stress, and that stress is zero because the total force is removed. Okay, but such is not the case with bending, because in bending, within the cross section, the stresses are different. Okay, everywhere in the cross section, the stress is different. So when you unload, and the unload happens elastically, therefore, um, the stress everywhere in the section doesn't reduce by the same amount. Okay, and that's when we end up having some residual stress. Now, can you get the expression for delta sigma? It would be some function of y. It would actually be proportional to y. So unloading is happening as if you are doing, as if you are getting an elastic response of the beam, okay, but in negative. Okay, you will have to treat that FUL just like that is causing some amount of elastic deformation in the beam, and then you'll have to get the stress corresponding to that FUL, and you'll have to subtract that. Okay, so because the second part of the analysis, okay, you started with certain initial set of stresses. Okay, when you are over here before unloading, you started with certain initial state of stresses. Okay, and then this process is simply elastic and linear. So you can do some linear superposition. Basically, the stress you can directly subtract. So you can consider just an one linear operation is happening, and that stress you are simply subtracting. এই পার্টটা কি বোঝা যাচ্ছে কি বলছি?
আচ্ছা লাস্টটা কি বললেন?
হ্যাঁ,
লাস্টটা কি বললেন আরেকবার বলে দেবেন?
হ্যাঁ, মানে আমরা এখানে আনলোডিং করছি, তো the unloading process is elastic. Okay, and actually the span of elastic unloading extends in the compressive side as well. বুঝতেই পারছো? So the limit on unloading is twice sigma y, whereas when you were loading from the origin, okay, by the time you reach sigma y, you started having plastic deformation. So the entire unloading process is going to be elastic, no doubt in that. Okay, now because the second part of the process, I mean, so the loading part was elastoplastic, but the unloading part is simply elastic, and that to linear elastic, you can do linear superposition. So whatever stress you got at the end of, you know, elastoplastic deformation, okay, so you applied certain F value okay, to have the elastic core of certain size, let's say h by 4. Okay, so you know uh, mm, uh, adjusted erode AF such that you have the elastic core of that size. Okay, so that part has ended, the loading part has ended. So you have got certain stresses due to that loading part. Okay, so in the elastic core you have certain stress, in the plastic shell you have certain stress. Okay, so that you have got at the end of the loading part. Now that you are unloading, which is a linear operation, linear uh, you know linear deformation, elastoplastic deformation, sorry, elastic deformation. So now you can think of this happening, what happening, that there is some initial stress which you got at the end of the loading part, and there is certain stress that you would have got if you had loaded the system, okay, with that same force. Okay, but this time only elastic deformation happening. This time uh, the material doesn't go to plasticity. Okay, now the second part, okay, of the stress distribution, the stress distribution of the second condition where the material doesn't go into plastic deformation, okay, that actually you need to think of is happening in reverse, as in unloading, and that you'll have to subtract from the current stress state to get the residual stresses. Now, have you got the expression for delta sigma? Delta sigma expression টা পাওয়া
4
যায়?
sigma into
Yes, sir.
h by delta
Okay.
sigma 4 into sigma
Okay.
into L
Let me finish.
by.
Let me finish. You will have the expression for delta sigma with y in it, which basically means it is a function of the distance from the neutral axis. Okay. So the earlier expression for stress at the stress distribution that you have at the end of the loading phase, for example, within the core, it is sigma y times y divided by c, or for the example that we are choosing, that is c equals h by 4, that expression is 4 by h sigma y times y. Okay, so from that subtract whatever expression that you have got. Okay, and in the second expression, which is outside of the elastic core, from that also subtract the expression that you have got. That would be the stress within the elastic core and in the plastic shell after complete unloading of the beam. So the idea is that instead of loading elastoplastically, if if the material was completely loaded elastically, it would have some other stress distribution, right? Maybe slightly extending over here beyond sigma y, maybe extending a little over sigma y in this side. And because the stresses are higher at the two ends, you know, over here the stress would be a little smaller, and it is changing linearly. Okay, now this green part you'll have to subtract from the red part. Okay, so your region of consideration is this portions. these are going to be your residual stresses. So this is going to be your distribution of residual stress with y coordinate. So that is your second assignment. Plot with respect to y. Now, your argument should be, how can the stress on the material go beyond sigma y? The answer is, it is actually not. We are simply considering from plus sigma y to, you see the elastic window while unloading is of twice sigma y. It can go from plus sigma y to minus sigma y. It's with respect to this plus sigma y am I considering developing a stress. I'm actually considering the unloading. And because the unloading process is totally elastic, I'm considering what sort of stress I would have got if I had applied the same force that causes, elastic core of certain size, okay, and the material would have, deformed elastically. So that stress I'm calculating, okay, and that stress needs to be subtracted. The material actually not going beyond sigma y. এই পার্টটা কি বোঝা গেল?
না
হ্যাঁ
স্যার
বোঝা গেছে?
একবার বলুন, ওই ছিল
কোন
স্যার
পার্টটা বোঝা
একটু
গেছে?
আগে কথা খুব কাটছিল অনেক টাইম ধরে।
কোন পার্টটা শুনতে পাওনি বা বুঝতে পারোনি বলো একবার।
এই যে ডেল ওয়াইটা সাবট্রাক্ট করেছিলেন আর অ্যাড করেছিলেন, ওইখান থেকে কথা কাটছিল।
No, the point is that this is the stress distribution, the rate curve that you have got through elastoplastic deformation. But if there were only elastic deformation, we would have got that green curve, okay, and because the unloading is completely elastic, so the green curve represents the reduction in stress in the unloading process. So the green curve must be subtracted from the red curve to have the residual stresses. And your assignment number 2 is to plot the residual stresses with respect to y. Is it clear now?
Yes, sir.
Okay. I have just one more thing to say. So we talked about reaching certain
রেসিডুয়াল স্ট্রেসটা বেশি কি করে হচ্ছে সিগমা ম্যাক্স এর থেকে, ওইটা আবার বলে দেবো।
অ্যাকচুয়াল রেসিডুয়াল স্ট্রেসটা কিন্তু সিগমা ওয়াই এর থেকে বেশি হতে পারে, সিগমা ম্যাক্স না, সিগমা ওয়াই এর থেকে বেশি হতে পারে। ওকে, কেন হতে পারে? বিকজ this is your elastic unloading window which has a size of twice sigma y. It can go from plus sigma y to minus sigma y. Okay, so that's why the residual stress can be the stress reduction can be more than sigma y. Okay, because the unloading process is completely elastic. So you unload the force that you use to have the elastic core of certain size, but while you are loading you had elastoplastic stress distribution. When you unloaded, it is only elastic stress distribution that needs to be subtracted. Okay, so the green curve is not stress distribution, it is the change in the stress distribution. The red curve is the stress distribution after the loading process. The green curve represents the change in the stress distribution after unloading. Change. Okay.
Okay.
The net and the net stress distribution is in the right. Okay, which represents the residual stress. Because the loading part was elastoplastic and unloading part was elastic, there would be several pockets in the cross section where there would be positive and negative stress states locked within the material. মানে simply material মধ্যে locked. There is no one who can take those stresses out. I mean, yes, there are processes to do that, but not just mechanical process. Okay, you'll have to, heat treat that and something else. Okay, so that's why we say, right, when a material has been forged, okay, যখন আমরা forging করি, it develops compressive residual stress. And actually তোমরা হয়তো শুনে থাকবে যে when there is a welded joint at the welding, okay, to make it stronger against crack propagation. Okay, crack propagation is the problem of tensile loading. ঠিক আছে, compressive loading এ crack propagation হয় না. So what do people do? They hammer welded joint, or fire metallic balls, hardened metallic balls at the welded joint to incorporate residual compressive stress. So residual compressive stress is a reality, and residual compressive stress is of great significance. Okay, we need that. So by incorporation of the residual compressive stress, they take the stress state locked. I mean, even after balls have hit the weldment and they have left the region, the stress states there would still be compressive. Okay, because in some other location it would be tensile. So having that compressive state frozen in the weldment, how does that help? When you try to when you load the welded joint, and in some place there is tensile stress state developing, then it has to go from negative value to first to zero value and then to tensile side, thereby reducing the chances of failure, thereby giving it a the opposite of head start. I mean, it is sent a little in the compressive side. So when it is loaded in tension, it to reach any positive tensile stress value, it has to first overcome that compressive zone. Okay, while loaded in tension. So that actually helps the structure against failure. Okay, so that's the idea behind the residual stress. But there is one more thing I would like to talk about, and that is we just talked about having F star, which is the load bearing capacity. So what happens to the beam? We also talked about that the beam loses its stiffness. Now, what sort of stiffness? Stiffness against bending. It just becomes zero when you reach that F star value. Okay. So imagine F reaches that F star value. Okay, and this cross section right here has completely become plastic, and it can no longer bear any additional amount of load. Okay, this given cross section has no moment bearing capacity. Okay, it cannot support. You see, the stress is due to bending moment, right? Okay, stress is due to bending moment, so it cannot support any further bending moment. Now you can imagine the left side of the beam and the right side of the beam is joined by are connected by a fixed joint. Okay, a fixed joint which can support Rx, Ry, and a moment. Okay, now in this joint, okay, the moment bearing capacity is lost. It has become zero because the entire section has become plastic. Now it can support maybe Rx and Ry, but it can no longer support bending moment or any moment. Okay, So you have now a fixed joint which cannot support moment but only support Rx and Ry. Then what sort of joint has it? We'll meet on Wednesday.
Okay, sir.
Okay.